Okay, so what we are going to do today is to talk about, we will pick up where we started. I will recap some of the things. We are going to talk about phase diagrams. We already saw one phase diagram, which is the phase diagram of water, right? It was a single component system. So we want to make it a bit more complicated. We want to talk about phase diagrams of two component systems. And we will look at two example systems, two very typical phase diagrams. Of course, phase diagrams get infinitely more complicated, but these two cover a lot of interesting concepts. And if you understand these two, then you should be able to understand any phase diagram. Basically, that's the idea. So these are, and you can also generalize it to a three-component system. It's not much harder. So for a two-component system, we are going to study two types of phase diagrams. The first one will be fully mixable with two phases. And we are going to call these phases as liquid and vapor. It could have been liquid and solid, it could have been solid and vapor, doesn't matter, okay? Two phases, two component system with two phases which mix entirely, okay? You can keep adding as much as you want, it will mix. What is the best example of such a system? Who here likes to drink whiskey? Must be someone, you know what I mean, right? In whiskey, you can keep adding water. The water never comes on top, right? It keeps mixing. So alcohol and water are the perfect example. If you add 1 drop of water to alcohol, it will mix. If you add 50-50 alcohol water, it will still perfectly mix. You will not find that there is half alcohol and half water, right? The second thing that we are going to study is partially mixable. What if they don't mix? In the sense that maybe they mix in a little bit amount, but if you add too much of it, they start to separate and you see two different things forming. So partially mixable. And in this case, we will study only one phase. We will call it just liquid. And when I do this, you will see why we are doing only one phase for this one. You can generalize it to two phases and you can make it more complicated. What is an example of partially mixable with one phase? Oil and water, or water and milk, right? I told you my childhood story. Example, oil and water, right? Oil and water do mix in small amounts, right? But it's a very, very tiny amount as soon as you add. What other example can you think of partially mixable systems, not necessarily liquid? Anything that is supersaturated, which is, I mean, supersaturation is an example of partial mixing, right? So most things will be partially mixable. They will mix to some amount and then they will stop mixing. It could be a material in which you're putting some defects, and at some point the defects just become their own. If you mix copper and zinc, for example, it could not be. So most things will be in the second category. First thing is really not, actually a lot of things are also in the first category. So, you have to see what it is. Yeah, like I say, most things will be second category. Then I realized, no, actually quite a few can be in first also. But between these two, you can cover a whole lot of phase diagrams. So we'll work on both of these. So, and I also want to remind you that though we don't really need the regular solution model to work through this, it is useful in order to understand this. And let me remind you of the regular solution model. Mixing Gibbs free energy of mixing. That was delta mixing H minus T delta mixing S, right? And we said that for ideal mixing, delta mixing H is 0, right? And we calculated delta mixing S using a pair model, right? And delta mixing H for the regular solution model was omega XA XB. And delta mixing S was always this particular term, XA ln XA plus XB ln XB. So we are going to use this as a motivation to understand how things go, especially for the second case, for the partially mixable case. So in this, we studied two cases, just to recap. We studied omega less than 0 and omega more than 0. At omega less than 0, low temperature or high temperature, both terms are negative, right? If omega is negative, the mole fraction is always between 0 and 1, right? So the product of mole fraction is always negative. The second term, the entropy term, is also always negative, right? So if omega is less than 0, the free energy of mixing always looks like this, right? At any temperature, low temperature or high temperature. So if the regular solution parameter is negative, things mix perfectly. So this setup, omega less than 0, is a good setup to describe our fully mixable liquids, okay? For partially mixable liquids, we are going to use the second setup, which is omega more than 0. In this case, if you recall, there was a competition, right? And you can already see if omega less than 0, then competition between delta mixing H and delta mixing S. At very low concentrations, delta mixing S dominates. Why does it dominate? Because of log X term, right? Log X just drops down. So even if you are partially mixable, you will mix for some amounts, right? Even oil and water, if you had 1 drop of oil in a bucket of water, it might mix, who knows? It depends on it. And this tells you that it will mix for the tiniest amount. Maybe even a drop is too big, but for like a nano drop of oil, it will mix. But depending on temperature, you have competition, right? So there we studied 2 cases. We had low T and high T. Actually, let me write it down in the other order. We had high T and low T. At high T, entropy dominates, right? In this term, in this equation. If temperature is too high, the effect of the enthalpy term does not matter. The entropy term only dominates, right? So at high temperature, even omega positive tends to look like this one. At low temperature is where we started to see competition, and we saw something that looked like it had a cusp in between, right? Because of the competition between delta mixing H and delta mixing S. So this is just a recap, and we are going to use both of these to study what happens next. So let's go to the first case, the fully mixable with 2 phases. So what I'm going to do here is to draw, I will try to do everything in this page. So I'll write a bit smaller. So I'll draw a phase diagram where the x-axis is composition of B. It goes from 0 to 1. And I'm going to have five different temperatures. Okay, I'm going to call them T1, T2, T3, T4, T5. And I want to study that for this system, which is fully mixable how do liquid and vapor compete with each other as a function of temperature? And of course, if you make the temperature even lower, then solid should form, right? So we are not going to that far now. We are just going to talk about liquid and vapor. So at very, very high temperature, which phase do you expect to form? And this is at constant pressure. All of this is happening at a constant pressure, right? So now if you fix a temperature and pressure, what is the state function that you should be looking at? It gives free energy, right? That decides spontaneity. And someone made a comment on the plates example on Slack. Who made that comment? He's not here. Huh? What's his name? Rohan made that comment, right? The entropy should be maximized. Be careful. It's not a closed system, right? So you have anytime after this course, you should not just say entropy is maximized. You have to look at the control variables. If it's truly a closed system, then equilibrium means maximization of entropy. Otherwise, no. Okay. So in this system, at very, very high temperature, do you expect the system to be liquid or vapor? Vapor, right? If you heat something, if I take her and heat her, she will probably vaporize, right? I'm sure she will vaporize. So at very, very high temperature, it's going to be all vapor. At very, very low temperature, again, not so low that solid starts to form, somewhere like for water, somewhere between 0 and 100 degrees Celsius, okay? Everything is going to be liquid, right? Across composition range. Everything is going to be liquid. What we want to understand, what happens in the middle, okay? So first, let's start with the very high temperature at T1. At T is equal to T1, I want to plot the delta mixing G for the liquid phase and for the vapor phase. Since liquid is at T is equal to T1, vapor is always going to form, and we are talking about constant temperature and pressure. What does this tell me about the Gibbs energy of vapor with respect to the Gibbs energy of liquid? Which one is lower? Vapor, the one that forms, right? So vapor is always going to be lower than liquid. Furthermore, at what is going to be the delta mixing of G at both ends? It becomes zero, right? There is no mixing. You're talking relative to the pure compounds, right? So both of them will start here. This is the zero line. And in the middle, they will drop down because we are talking about fully mixable systems. So it's always going to be negative, right? And for liquid, it's going to be something like this. For vapor, it's going to be something like this. Because at any composition, we know the temperature is so high that vapor is more stable than liquid, right? So vapor always has to be lower. And at both ends, both should meet zero. Okay. That is T is equal to T1. This just shows that at any composition, this is XB is equal to 0 to XB is equal to 1, vapor is more stable than liquid. Now, let's go on this end at the bottom of the page to the very, very highest temperature. T is equal to T5. At T is equal to T5, what do you expect these two curves to look like? At T is equal to T5, which is the more stable phase in this phase diagram? That's liquid, right? So what should happen to the two curves? They should just switch, right? So now I will have some, and I'm drawing these qualitatively, but the basic picture is correct. So now this will be vapor and this will be liquid, right? So the question is what happens at T is equal to T2, T3, T4? Okay, let's try to understand it carefully. In order to do it, we have to go to our fundamental relation for G. Anyone remembers what are the natural variables for G? NPT. You're a good person. Now tell me the fundamental equation for DG. VdP minus SDT plus mu dN, right? And we are talking about, so that is the fundamental equation, right? So what we are trying to understand is that at a given composition and at a given pressure, how would free energy change as a function of temperature? Okay, what is that quantity? That is partial G by partial T at constant P and N. And here N really means Na and Nb, right? Xa and Xb, the mole fraction. This thing is minus S, right? What does this tell me about Gibbs free energy as I lower the temperature? And we are going to use the third law of thermodynamics here, right? Third law of thermodynamics says that the entropy is always positive. So what is minus S? That is always negative, right? So if partial G by partial T is a negative number, what does it tell me about change in G as you decrease T? It should be positive, right? If delta T is negative and that means delta G is also negative, then the ratio will be a positive number, which is not possible, right? So this means G increases as T decreases, okay? Because this is always negative. Furthermore, entropy of vapor is more than entropy of liquid, right? So physically, what are we saying here? We are saying that as you decrease the temperature, both free energy curves will move up, right? Because if delta T is negative, delta G is positive. So both free energy curves have to move up. Which one will move up faster? SV is more negative, right? Minus SV is more negative. So the vapor curve, GV will move up faster than GL, okay? It's just simple algebra from which I'm drawing this conclusion. And we have seen this previously also when we looked at phase transitions. And if you compare this bottom right figure with the top left figure, you can see that is what has kind of happened, right? We moved up above L, and you can see that we moved up above L, right? So at an intermediate temperature, and I'm going to draw it only for one temperature. I will draw only for T3 because you will see it's a bit of work to draw, and then you will be able to see what happens at T2 and T4. It is kind of similar. Let's just pick T3. T is equal to T3, and let's draw a bigger box here. The axes are the same. XB is equal to 0, XP is equal to 1. So as you decrease the temperature, both of these curves have to move up as T decreases, right? As you go from T1 to T3, both of these are going to move up. And vapor is going to move up faster than liquid. So what does that mean? In this case, you have seen that vapor has moved completely above liquid and has surpassed it at all concentrations, right? What do you expect to happen somewhere in the middle? It has moved up, and maybe it has surpassed it in the left half. Maybe it has surpassed it in the right half, right? Maybe it has surpassed it somewhere in the middle, right? It's not going to, you have two cars. You have, it's best explained with hands. So you have two cars like this, and both are moving up, right? Initially, you were like this, and finally, you are like this. In the middle, as it moves up, unless the curves are identical, you will have some behavior like this, right? When they cross each other. And they could be very well identical, then there you have bigger problem. Like, why are the liquid free energies and vapor free energies exactly identical? That's a rare event. That's extremely unlikely. So I'm going to draw a hypothetical curve as to how it's going to look. It's going to look, and I will use two colors here. So the vapor has moved up. It's going to look something like this, and it has crossed the liquid in some parts. So here, this is liquid, and this is vapor. And it could have been the other side. You know, here I'm showing that vapor has surpassed liquid for high mole fraction of B, but it could have been the other way around. Maybe the vapor moved up on the left side, right? It's just an example of how it would look like. This will lead to asymmetry in the phase diagram. Okay, everyone with me so far, mostly? Yeah. For the general case, if you want to make it symmetrical, up to you. You can. It's rare to find symmetrical things. Most of the time it is asymmetrical. Okay. I think there are some systems for it. Argon and xenon will probably be symmetrical. You know, if you go to rare gases. Otherwise, there will always be some asymmetry depending on the chemical nature. And I don't know which is A, which is B. So just general case. So now my question for you is, and I have to zoom in here, okay, because we are going to look at it carefully. So this is liquid and this is vapor. Looking at these two free energy curves at an intermediate temperature, what can you say about where should the system be vapor and where should the system be liquid? At XB is equal to 0. At XB is equal to, let's say, 0.1. Should the system be vapor or liquid? Why? Lower free energy, right? And how about, let's draw a black curve for this. How about 0.9? It should be all liquid, right? So as per this, you might be tempted to conclude that everything until here should be vapor, right? And everything on the other side of it should be liquid. Is that an okay conclusion? But something very interesting happens. I'm going to do next what is known as common tangent construction. This construction was introduced by Maxwell. If you have done any electrodynamics, you remember Maxwell's laws, kind of 4 laws, which are so important. Not many people knew he had other interests also, like thermodynamics, and he did this common tangent construction. Maxwell said, if you have two curves, let's talk about geometry for just a little bit before we come down to phase diagrams. Okay, I want you to do an exercise. At any given point, and again, I'm going to do it. If I think one person is on Zoom, so I'm sorry if you're on Zoom. At any given point on this curve, you can draw a tangent, right? Let's say you are at this point. How many tangents can you draw here? Why? It's the slope. There's one slope, right? There is only, what is a tangent? A tangent is a line which does not intersect it anywhere, right? Just touches it over there. Here also you can form a tangent. Here also you can, for the red curve also you can form a tangent, right? So to the blue curve, you can form lots and lots of tangents, right? Maxwell said there will be a very, very special line that is a tangent to both the curves at the same time. And for these curves, there can be only one such line, right? You can draw it over here. It's going to look something like, right? You can work through the math and see that there is going to be only one such line for free energies like this, right? If these free energies have non-trivial behavior, then this story changes. But for these free energies, there exists one and only one common tangent to both the curves, right? And if you really want to show it, start with two parabolas and you can see. This is really a linear equation that you're solving, okay? So this is common tangent. Why do we care about this common tangent? A tangent is given by this slope, right? That's what characterizes a tangent, right? Slope of what? What is the curve that we plotted here? It is free energy, right? So we are talking about derivative of the free energy. Slope here is derivative of the free energy with respect to concentration. Does it have a name? Lydia should be able to answer this question. She is the guru of this one now. Yeah, there we go. Partial G V by partial X B is mu B in the vapor phase. Okay? This is the definition of chemical potential, right? Partial GL by partial XB is the chemical potential of B in the liquid phase, right? And what you have just shown by drawing this common tangent is that these two things are equal, right? That is the meaning of common tangent, right? Both slopes are equal. And if you have two chemical potentials equal, that means liquid and vapor can exist together in equilibrium, but not all liquid and all vapor. Vapor of concentration XV can exist in equilibrium with liquid of concentration XL. Okay? Why does this matter? And I will go through this argument again. There is a bunch of ideas here. So you all told me that until this point over here, the blue curve has lower free energy than the red curve, right? Everyone agrees? And after this point, the red curve has lower free energy than the blue curve, right? The argument I'm making is, let's say you are at this point, okay? And you're very happy here. You're like, aha, I have lower free energy. I'm very happy. What I can do is to come down from this to this line, to this point, okay? Let's call this happy point as point R, and let's call this new point as Q. You will be like, well, Q doesn't lie on any free energy curve. Q doesn't lie on red. Q doesn't lie on blue. But there is something special about Q. Q is a linear combination of this and this, right? Q is an exact. Q corresponds to a system where you are neither liquid entirely, nor you are neither liquid entirely, you are not vapor entirely. You have split into a system which is made up of vapor with this concentration and liquid with this concentration. Why can you do that? Because their chemical potentials are equal. So they can exist in equilibrium with each other. And as soon as you do this, your free energy has been lower. Okay? So what's going to happen is between these two, between XB is equal to 0 and XV, the system will exist as vapor. Between XV and XL, the system will exist as vapor plus liquid. And then finally, to the right side of XL, it will exist only as liquid. This is liquefaction. As you start, in physical chemistry in your undergrad, if you've taken any PChem, you have probably done Liver's rule, which we'll be visiting later. Liver's rule uses this exact fact, and PChem we always just start using Liver's rule without realizing it comes from all of this business. Let me go through this argument once again from beginning. At very highest temperature, T is equal to T1, we all know the system is going to be fully vapor, right? So it's going to look like this. The free energy of vapor is always lower than the free energy of liquid, right? At very, very low temperatures, the system is going to be all liquid. So liquid free energy is lower than vapor, right? And you can see that partial G by partial T at constant T and N. So at any concentration, at constant pressure, if you decrease the temperature, the free energy goes up because S is positive, so minus S is negative. Vapor has higher entropy than liquid, so for vapor it goes up quicker. So for part of this system, vapor will go above the liquid curve. So the vapor moves up and it crosses the liquid curve. I want to be a general case, so I just do a symmetric where it happens on the right side of XP, you do it on the left side, who cares? Same story. It went up here and you get a crossing point. If you get a crossing point, if you now naively look at it, it seems like the free energy of vapor is lower than liquid until the crossing point, which it really is, and the free energy of liquid is lower than that of vapor until this point, starting from this crossing point, but that's not the full story. Because if you are in the middle of this crossing point, you would like to be here on the blue curve because the free energy is low. But instead of that, if you drop down to the Q curve, and let's drop to the Q point, and let's write down what is special about Q point. At Q, the free energy of the system now becomes combination of vapor with mole fraction XB, XV, and liquid with mole fraction XL. Okay, so at any point between here and here, the system will always separate into a vapor and a liquid. The subtle thing here is whether you are here or 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 here, any of these regions along this one or this one, you will separate into vapor and liquid. The subtle point is the concentration of V in the vapor will be the same. Does anyone remember this from basics like high school chemistry, why this matters? In a process involving also alcohol. Fraction distillation, right? Any vapor that comes out always has the same concentration of alcohol, right? What will change between here and here is the amount of vapor and the amount of liquid you form, right? If the smiley was to move to this point, just to the little right of this black point, again you will form vapor with this concentration and liquid with this concentration over here. But how much liquid will you form and how much vapor will you form at this point? Almost entirely vapor, right? Because you are so close to it. If you are exactly at this point, then 100% vapor, right? If you are exactly at this point, you will form 100% liquid. Liver's rule gives you a formula for calculating how much vapor, how much liquid you have. Next class, okay? And why is the common tangent special? Because we are saying that the vapor and liquid have to coexist with each other. And the second law of thermodynamics for coexistence of phases says that chemical potential must be equal. And chemical potential is equal. Chemical potential is the derivative of the free energy with respect to concentration, right? And that is equal only along this common tangent. Go ahead.
So why is is it only in the region between those 2 points?
Because there is no advantage. If I go over here,
Well, the tangent line is still lower than.
yeah, but that's what's going to happen. You will form a vapor, and then what else on the left side? Nothing. To come from here to form something in the middle of these two, right? This is South Pole. There is nothing on the other end. Backward. Here, what will you separate it? Look at physically what's happening. You're at this concentration, right? What happened here is that the vapor phase gave up some V atoms to the liquid phase, okay? And the liquid phase gained some V atoms from the vapor phase. Here, there is nothing like that going on. You could drop them a line, but what are you going to do? Where will you move? There's nothing. You need to have a phase. Go and draw this thing, you will see why it makes complete sense. There's nothing to separate between this. You can have the separation only happen between this point and this point. Let's take another example here. Okay, here you are probably convinced that nothing is going to happen because the only tangent you can have here is never going to be common tangent, right? So the reason this is confusing you is because you are thinking that if I'm at this point, why don't I drop down to this point, right? So okay, let's say you drop down to this point. You form one phase which has this concentration, but my question is, where is the other phase going to come from? There's nothing over there, right? If you went from this point to form here and here, then the amount of V has increased. You cannot do that, right? Keep that in mind. For the principle of atom conservation, right? Conservation. So some V decreased, some V increased. If you do over here, both will have to increase in V. That's simply not possible. Any more questions? Yeah.
So what happens in the case where they overlap completely? Would it just be
It's boring.
vapor in
Yeah, it's
but
boring.
would it just be an equilibrium?
It will be super boring. So boring, I want to sleep. Looks like it's a problem I can give you in the front. It will be like this. You can make the limit of it. Once I draw the phase diagram, you will kind of see a sense of what happens. Okay. Yeah, it'll look boring. So this thing, common tangent construction, I just drew it here. Online you will find tons of articles explaining this in great detail. So if it's confusing, go and just Google and look up the first thing that comes up. Okay, and it's not going to be hard. However, I think working through this carefully gives intuition, and especially you can't really talk about common tangent construction until you have a better feeling for the chemical potential, right? Chemical potential is the hero of this game, right? So I was very glad when you asked about chemical potential last time, because if you, and I know chemical potential is perhaps still a bit esoteric to some of you or maybe all of you, but if you didn't understand this relation, then there's no point in doing any of this, right? It just doesn't make sense. So if now I go to T3 and I want to write down V and liquid, what am I going to see in this phase diagram? On the very left side, it's again going to be V. On the very right side is again going to be L, right? And in the middle is going to be V plus L coexisting, right? Okay. If you were to do this operation at T2 and T4, you will realize it's a similar behavior, but it's going to look something like this. V, V, V plus L, L. So you can see what's going on here. Let's look at this one. So you have V plus L in the middle. Here also you have V plus L in the middle. Here you have also V plus L in the middle. But given the asymmetry in the phase diagram that I drew, as the temperature decreases, they keep moving to the right. Okay. So now if you join the boundary, and I will draw this phase diagram on the next page, you will get something that looks like this. You will have a boundary that looks like this between vapor and liquid. Okay. This all happened due to the mixing of free energy being completely negative at all temperatures, right? This curve was such that if you did not have a competition between vapor and liquid,
So the
lower always dominates.
So the lower the temperature,
the lower the temperature or higher the temperature, life becomes simple. Life is complicated in the middle temperature, which is true in thermodynamics all the time, right?
So for example, for in the homework, when you're already asking to give you the temperature, to convert that to the Gibbs.
Yeah.
So that's what I'm asking.
Yeah.
How
You will do that. It's 60 points. Oh, yeah. I did something terribly wrong here.
Is the bottom all liquid?
Oops, sorry. Yeah, good spot. Well, I have to be careful in the phase diagram that I drew. State consistent. 1 second. Nope, I made a mistake here. This lens in this one, sorry, you can cross that. The lens is going to be opposite direction. So again, at very high temperature, it is all vapor. At very low temperature, it is all liquid. And as per this free energy at intermediate temperature, it is vapor on the left side, right? I have to follow my free energy always, right? Free energy tells me that at very low concentration, it is vapor, okay? And then it is vapor plus liquid, and then it is liquid. So the lens is going to be like this. Now it's consistent. Sorry about that. The first homework problem is easy. If you pay attention to today's class, you will see it's basically this part and the second part done together with a little bit of change. Okay, everyone happy now? No? Oh, wow. Tell me.
The common tangent only exists.
Yeah.
Okay, so should we draw it across those points?
That's a good point. That is what causes that was what was causing Ben's confusion. So this is confusing, right? That's what you're saying.
Yeah.
Sure. I no, there is nothing wrong in drawing it. It's just that you cannot drop down the
What if it's
composition.
not like atomically- if it's not like a-
But the line exists, right? The common tangent is a
Your
line.
system can't like actually embody that.
No, it cannot, but I can always draw a straight line, right? I can draw my straight line down, no,
But it's like a physically meaningful.
like here. It's just a straight line. Physically, it's meaningful only between those 2 points. That's correct. That was exactly the point. Okay, so if it confuses you, why did I change the shape of the lens? That comes from the fact that the vapor is on the left side. That comes from here, right? And as I increase the temperature, I expect more and more vapor to form, right? That's why the lens should be like this, more and more vapor. Now, if the vapor had gone above the liquid on the left side, then the lens would be faced the opposite. If it was symmetric, the lens would be in the middle, right? The lens would be symmetric. So the ethanol water phase diagram, let's look it up. Mostly looks like that. There is some funky business happening over here. That's not really. But you see that behavior, the lens type behavior that happened over here. This is, yeah, this is not too hard. This is a good funny problem. Huh?
Is that the eutectic one?
Yeah, similar. So this is a fully mixable liquid. It's actually called the azeotropic point, but it's one of those funky points where funky things happen. Yeah.
This chemical potential here that depends on the phase, is this also an extensive quantity?
Sure, I've been sloppy here. So in principle, I should multiply it by total number of atoms, n. There you go. So the true definition of chemical potential is, let me write it this way. The true definition of chemical potential is right, then it's not extensive, then it's intensive quantity. Chemical potential is never extensive, it's intensive. So what I did earlier was to not divide by NB, I divided by mole fraction because the total number of atoms is constant. So I did over here.
Okay, that it's not gonna depend on, only it's dependent on N, nothing else. That's what I meant, but
It depends on not N, it depends on the ratio of NB. It depends on where you are along the line.
like mole number. let's
Yeah.
say. So in this case, does it also be dependent on this
What this?
entropy?
Sure, it could. I'm not getting into that discussion at this point, so why is that bothering you? I mean, mu is a state function, right? So you are saying what are the natural variables for mu?
Because we, as of now, we know mu was.
It will depend. Okay, so someone asked this question on Slack. If you write a state function as a function of any three random variables, is it a state function? Is it a fundamental equation or not? So mu is g divided by number, right? What are the natural variables for g? NPT, right? So the natural variables for mu are p and t because you have removed n. In reality, it is, yeah. So you talk about chemical potential of something without talking about what are the number of other things, right? So mu depends on p and t. If you want to make mu a function of entropy, you can. Why would you like to do that?
I don't know, because it's the slope. How fast does the slope is changing depends on the.
But I'm talking about a fixed concentration. Fixed. If you really want to be rigorous here, and I said this, I did not write this, we are really talking about fixed Na and Nb. At fixed, and that is the slope. Okay, that's what it comes from. So this page is a lot of information. If you understand it, it's very trivial. And I don't say that loosely because like when I was in my undergrad or when I first did it, it took me a while to understand it. And then when I understood it, I never forgot it. It's really simple and it's kind of elegant because it uses a lot of things, right? It gives you something which is very practical. So that is a fully mixable liquid. And I want to emphasize again that as Ben and Anjali both pointed out, this common tangent really means something only between these 2 points, right? If you're to the left of it, doesn't make any sense, right? If you're in the middle, what's really going on here? And you can write this down if you wish. You are separating into A rich vapor and B rich liquid, right? Because the mole fraction of B is lower in the vapor. So it's richened in A. And liquid is richened in B. And the concentration of A in the vapor does not depend as to where you are in between these 2 points. That concentration is always going to be the same. It's the mole fraction of vapor and mole fraction of liquid that is going to change, right? So in a two-phase, two-component systems, we are really talking about 4 different mole fractions. We are talking about mole fraction of component A, mole fraction of component B. We can also talk about mole fraction of liquid and mole fraction of vapor, right? We can say how much of the system is liquid, how much of the system is vapor. So when we get to Liver's rule, we will be talking about all of these 4 mole fractions. But for now, we are not doing that. Any questions? Yeah.
So is there nothing significant about the point where they cross?
It is, yeah, I know. You have high hopes. Welcome to Edward's life. What I'm going to do next is to talk about partially mixable liquids in one phase. Now, this is one of those topics that no one ever teaches in chemistry. And that makes me very, very angry and pissed and sad. Because this has become super important for so many things, for biology, for chemistry. Our whole cells inside our body exploit this property. Our cells exist on this basis. And liquid-liquid phase separation, which is now becoming like one of the, like if you were a PhD student in the let's talk about research trends. Let's imagine you were a PhD student in 1985. What would have been a hot research topic back then? Can anyone guess? Let's say physics or chemistry, something like that, or biology. What would have been the hottest research topic in 85? High temperature superconductivity, right? Everyone was talking about it. In 1989, carbon nanotubes started to show up, right? And everyone was talking about that. These days, it's liquid-liquid phase separation. That's what we are going to study next. And I find a lot of biologists especially talk about it, and they have never, I'm pretty sure if you go and ask them about relation between chemical potential and free energy, they would be like, what? And there is no way you can understand phase separation without what I'm going to show you next. So pay attention to this, because this might be the only time you see this. And it will show up in your research sooner or later. And then you will thank me and Pakala. Okay, so example, water and oil. Okay, we are just going to restrict our attention to liquid, and then we will talk about what happens. I will show you how the phase diagram for something like this looks like first, and then I will talk about the free energy. The phase diagram for partially mixable liquids, and here, once again, the y-axis is temperature, the x-axis is concentration of B, going from 0 to B, has a very characteristic dome shape, okay? And this dome shape is such that in the middle of the dome, inside the dome, you have a two-phase region. So P is equal to 2, okay? P is equal to number of phases. And on either side of the dome, to the left, to the right, to the top, you have a one-phase region, okay? So this top of the dome is a critical point. It is, this temperature is known as the critical temperature. Again, I'm drawing it so that XB looks like 0.5. I'm not making any claim. It could be to the left, it could be to the right, okay? It could be anywhere. Inside this dome, something else interesting happens. So the boundary that you're seeing over here, first of all, this boundary is known as the miscibility gap, okay? This boundary tells you whether you are going to have a single phase region or a two-phase region, right? So again, if you have oil and water, if you have, and let's say XB is equal to mole fraction of oil, right? So what this is telling you is that you, if, and let's say you fix the temperature, and you move at this temperature from left to right. This is telling you if that the mole fraction of B, amount of oil is smaller than a certain volume, you will mix, you will have a single phase region, right? If you go in the middle, you will have a two-phase region. And again, if you add too much oil, then it will become one phase region. That's what you're going to see, which is something that happens in practice. In the middle, you have two-phase region, and inside this dome, there is a secret dome. And that secret dome, I'm going to draw in a separate color. That looks like this. This secret dome is known as the spinodal gap. The only difference between thermodynamics on its own cannot distinguish between miscibility gap and spinodal gap. So thermodynamics on your own won't be able to tell you whether you're inside the spinodal gap or you're between the spinodal gap and the miscibility gap. I will tell you exactly what they are. They are really distinguished through kinetics. Okay, and we'll talk about that in just a moment as to what all is going on here. And again, we are going to use common tangent construction. So in order to do this, let's use our, in order to understand all of this, let's use our regular solution model as an example. We have delta mixing G is equal to omega XA XB plus RT XA ln XA plus XB ln XB. And we are now interested in studying the system where omega is more than 0, right? So if there was no entropy, A does not really like B. If it mixes, it says, I don't like you, go away. It's only entropy which encourages mixing to happen. And entropy does not matter at 0 temperature, right? So if you're an, is there anyone who here who is, you're all physical chemists, right? Or biophysicists or chemical physicists. There is no inorganic chemist in the class, right? Of course, it makes sense. Inorganic chemists don't care about temperature. They just do DFT calculation. They go like, entropy, who cares? Because at 0 temperature, there's no entropy, right? So you can run DFT calculations, just get your delta H and you're done. You don't have to worry about delta S. Who? You didn't hear me.
No, keep talking. It's actually pretty cool.
Well, this is why they don't put me on inorganic candidacy exams. They put me on one, and I started grilling the poor students about entropy.
I've learned all that I need to about it.
Yeah. So, but when you're who have you picked an advisor yet?
Yeah,
Who?
Dr. Sebok.
Huh?
Sebok.
Sandbox. So Sandbox knows all these things. That's good. But I'm not going to get into non-PC areas. But yeah, I have definitely had arguments, not just here, elsewhere also. Often a lot of chemists think about entropy in a very slapdash manner. They consider it as something which is either it can be ignored or it can be just added as some simple correction, which is the furthest from reality. So I'm a big critic of DFT calculations for that very reason, because they work at 0 temperature. And it's impossible almost to correct for higher temperature effects. And people, when they design catalyst materials, they only do 0 temperature calculations. And then they go like, and I have just proved this material is a better catalyst due to my 0 temperature calculation. Well, why should it work at 300 Kelvin? Why should it work at 1500 Kelvin? It's all about entropy, right? But that's a different rant. I mean, this class started with entropy, so it should end with entropy, right? This whole semester, it's all about entropy. So, and nothing against inorganic chemists, they're very smart. I like it a lot, but I just wish, in general, I think inorganic chemists and physical chemists, the boundaries are kind of terrible, right? In chemistry departments, traditionally there have been boundaries. This is inorganic division, this is physical division, this is biochemistry division. To the level that the biochemistry seminar happens the same time as this class. Like, I want to attend the biochemistry seminar. Why can't I attend? It's like, no, you are physical chemist. You don't need to attend. It doesn't work that way, right? And it's anyway. So let's think about omega positive. At omega positive, if temperature becomes infinite, then it doesn't matter whether omega is positive or negative, right? It's all about entropy, right? Then it will be perfect mixing, because entropy tells you just mix. Who cares? The more you mix, the better it is, right? Entropy is higher. It's omega more than 0. So again, for omega positive at high temperature, if you recall, our delta H of mixing was like this, right? Because omega is positive and omega multiplied by XA multiplied by XP is just a parabola now, right? It just goes up. And minus minus T delta mixing of S was negative. And so their overall sum was predominantly negative, right? This was delta mixing G. If omega is 0, if omega is positive and temperature is very high, right? Then this curve over here is going to be very, very negative, right? And it's going to dominate. You have a tiny parabola, but what's that going to do? It's like David Wilson's Goliath, right? That's what's going to happen. But if you have low temperature, that's when we saw interesting physics emerge. At low temperature, we found that does temperature affect delta mixing H? No, it's just omega XA XB, right? There is no effect of temperature. But now this minus T delta mixing S is going to be a curve that looks like this, right? It won't be that, I should draw that also in black. It won't be something that is far negative, right? It is somewhere up. And we know that at the ends, this is going to dominate, right? Again, that goes to our log X. And Jock, the undergrad, is here. I guess I can promote you now. When are you graduating? Like, you have 1 semester left? I still the undergrad. The L'Hopital rule proved us that. L'Hopital, no, is that? I'll just go back to the hospital. The hospital rule proved to us that at the limit, this curve is always going to dominate, right? Always remember that. It's so beautiful, right? It's simple math that the slope goes to minus infinity, which leads to such conclusions. So at this end, the net sum of this and this will always be negative, right? But in the middle, this might start to dominate, right? So I'm drawing qualitative curves over here. In the middle, you're going to get something that looks like this, qualitatively speaking, right? At both ends, it drops down, and in the middle, it starts to raise. You can already see the implication of this. You can already look at these and start to understand the phase diagram over here. At high temperature, things mix perfectly, right? So at high temperatures, you have just one phase. Everything is mixing perfectly. At low temperatures, something funky goes on, right? Delta mixing G has a non-trivial behavior. And if you have paid attention to the common tangent rule, that's what's going to happen next. But now we will draw the tangent in the same free energy curve. That's the whole game. Now we don't have two free energy curves. There are only one free energy curve. Let's see what goes on. So at low temperature, you can see now non-trivial behavior is happening. And you will see two phases. So let's try to understand that. So this is the one we are going to pay attention to. Low temperature, omega positive. And again, this is not restricted to regular solution model. I'm just using that as an example to motivate this. Okay. Any questions about this? No questions? Murray? No questions? Good. Yeah. And
So the top diagram is the phase diagram.
that's the phase diagram, which we haven't proved yet.
Okay, so we're looking in the low temperature.
Yeah.
So like the bottom.
Somewhere here or here, anywhere between below the critical temperature,
Okay. We're gonna use that energy diagram.
to explain why something like this happens. Okay, this I just spit it out there, just said like, believe in me, believe in this. But you shouldn't believe in that. But this you have seen through math. So I'm going to use this as an example to derive why this happens. So let me draw this curve in a much more expanded version. And I'm not going to draw delta mixing H or delta mixing S. Okay, I will only focus on delta mixing G. And this is going to be like a super massive one. Actually, let's draw the zero curve somewhere in the middle. The zero line does not really matter in this much. You will see why. Only thing we know is that now delta mixing G starts here, drops with a slope of minus infinity. Maybe it crosses up at some point, then it goes down, and then it again goes over here, right? This is the zoomed in version of the blue curve in the previous page, okay? So this is delta mixing G, omega positive, and low temperature. And let's mark the concentrations carefully in this one. So this is xp is equal to 0. This is xp is equal to 1. So and in this one, even though I drew the zero line, it ends up not mattering much. You'll see why. Now I want to play the common tangent game again. Okay. For this curve, at any point, I can draw a tangent, right? There is one and only one line, which is a tangent to this curve at 2 points. Does anyone see what is that line? It touches here, and here, right? It's like a ghost or something. So there is only one line, which is a common tangent So this is our common tangent. This is different from last time, right? Last time, what did we do? Last time we drew common tangent between two free energy curves, right? Because the free energy curves themselves were simple. Now we have one phase, but its free energy curve is complicated. So when you go to real chemicals, of course, it will be the worst of all worlds, right? You will have multiple phases with multiple free energy curves, which are super complicated. But it's just common tangent after common tangent after common tangent. There are softwares that do that. They go and find the best common tangents. Right? It's all about that. So, okay, let's call this concentration as X alpha. Again, X alpha is the mole fraction of B, not the mole fraction of A. Okay, that's how we have defined things. And let's call this one as X beta. Now, if I am at a point here, point 1, where my free energy is G1, I would be better off dropping down from here to this point, where I split into combination of two phases with mole fractions X alpha and X beta. Okay, so I will form one phase. The X alpha phase is now a B depleted phase, while the X beta phase is the B rich phase, right? And the free energy of this is going to be lower than G1. You can see that from the straight line, right? It's lower than that. And why can these two phases exist? Why can these two phases coexist? Chemical potential, right? What is the chemical potential of phase alpha? What is the chemical potential of B in phase alpha? Mu B in phase alpha is partial G by partial XB, right? Which is the same as mu B in phase beta over here. It's the same slope, right? So I think this is really beautiful that all of a sudden you have a single phase system in a two-component, single phase problem in a two-component system. But if you drop down over here, and what you're going to do is, so we are talking about liquids, right? We are talking about oil and water. So you started adding oil here. It's like, okay, you can add oil, As soon as you reach this point, the oil says, wait a minute, I'm not going to mix. I'm going to separate into one part, which is lower in oil. It still has some oil. It's not pure water, okay? It's not splitting into pure water and pure oil. So when oil and water separate out, go at home and do this experiment, and oil comes to the top of water. You don't have pure oil on the top of water, right? It's oily water. Similarly, water on the bottom is not pure water. It's watery oil. Watery oil on top of oily water, right? So at this point, it separates into water, which is lower in oil, but still has some oil, and oil, which has some water, but not that much. And this will happen at any of these points in the middle, right? And again, as Anjali and Ben are about to beat me up, this line over here does not really mean, right? I just drew it because it's a common tag, right? This process happens only between X alpha and this beta. So if you think about it now, you are going to have a liquid rich phase to the left of this, a liquid rich phase to the right of it, and in the middle, you are going to have two liquids, L alpha plus L beta, okay? And that explains this phase diagram, right? Part of the phase diagram. That explains the miscibility gap. It does not explain the spinodal gap yet. I will talk about that in a moment. Is this clear? I heard some loud sighs. Okay, I'll finish up soon. In this free energy curve, I have only one topic left in this. Let's identify two very, very special points, okay? This point over here and this point over here. These are my inflection points, okay? So until this point, the free energy was more and more positive, right? And after this point, the free energy is more and more negative, right? So this is the point where the curvature of the free energy goes to zero, right? Same thing over here. So these 2 points are points where double derivative of G with respect to B is equal to 0. And let me draw lines below these ones. Let's call this as X alpha S and X beta S. Something very interesting happens between these 2 points, and let's see if I can do a good job of explaining it. Now, let's say you are sitting at this concentration on the top, okay? And let's zoom in. From here, you decide to split into a combination of this concentration and this concentration, okay? Very, very tiny change, okay? You are at this concentration and you say, let's keep a little bit D away and let's give it to some other part. Tiny change, epsilon change, okay? Clearly, they are not going to exist in equilibrium, right? Why not? Because the chemical potentials are very, very different, right? So they can't exist in equilibrium. But what they did, if they could exist, the free energy would have been lower, right? So for any change you make in the system, even the tiniest fluctuation lowers the free energy. So you go here and you are like, well, I can't exist in equilibrium. But wait a minute, I can just go further out. I can split a bit more. I can split a bit more. And you can keep splitting more and more and more, even for the tiniest amount of fluctuations, right? And the free energy just keeps dropping down, down, and down, and down. So until these 2 points, tiniest amount of concentration fluctuation lowers free energy, just keeps going down and down. As opposed to over here. Over here, there is only one change in concentration which leads to energy going down. Over here, let me draw it. Again, by the way, let me clarify. On the exam or in the homework, I'm going to only ask you about miscibility gap. I'm not going to ask you about spinel gap or spinel decomposition, but so this part is not going to be in the exam, but please try your best to stay with me and understand it. So let's say you're over at this, let's color it in green, over here. Can you do a similar change as to what I did for a point on the green part? You cannot do that, right? If you make a tiny fluctuation over here, and I will post some extra notes on it, it's not necessarily going to lower the free energy. It's the tiniest amount of fluctuations lead to lowering of free energy only if you are between the 2 inflection points, okay? So physically, what does it look like? If your concentration is between these 2 points, okay, and you form, and let's say your water and oil mixed together, like existing together, and you form a tiny nucleus of oil, it will just keep growing more and more and more and more. While over here, if you're outside the inflection point, you have to have a fluctuation that is really big for it to be stabilized. Does that make sense? Not entirely.
So things happen going from one green.
So the point is that for whether, okay, let me emphasize one second. Whether you are inside these 2 inflection points, okay, or whether you are outside these 2 inflection points, as long as you are between these 2 points, the end is the same. You are going to form this and this, okay? There is only one common tangent which allows you to exist in equilibrium. So I'm not talking, that is why I said this is beyond thermodynamics, because thermodynamically it is going to look the same. You have a big A-rich blob and you have another B-rich blob, something like that. What I'm trying to distinguish is the process of that happening. Spinal, so that this what you saw over here is phase separation, right? This is known as this is liquid phase separation. But what I'm talking about is the kinetics of that process. If you're inside this, the tiniest amount of fluctuation still lowers the free energy. You cannot exist in equilibrium because that can happen only if you reach these 2 things. But anytime you keep lowering the free energy, anytime you have a small fluctuation, little bit of B goes from this point to this point, and at the cost of this one, the free energy goes down. Free energy goes down. So I will stop at this one. So basically, what you are going to see inside is the mechanism of phase separation that changes. So that's the main take home. So mechanism of phase separation in thermodynamics, we don't talk about mechanism, right? We talk about what will happen when we say something is spontaneous. We don't say when, right? We say if you wait long enough and your system is big enough, it will happen, right? What I'm showing you here in the process of going over there, how will it look like? So the mechanism of phase separation inside spinodal gap versus inside miscibility gap will be different. Outside miscibility gap, there is no phase separation, right? This means nothing. This means nothing. You're going to exist as a single. Only inside these two that phase separation happens. Outside the miscibility gap, you have what is known as nucleation and growth. And inside spinodal gap, you have what is known as spinodal decomposition. So spinodal decomposition is such that even the, again, I'm repeating myself, the tiniest amount of fluctuations still have lower free energy. Over here, you cannot do that, right? Actually, it's simpler than what I'm saying. Let me draw this over here. Let's say you are at this point and you decide I'm going to separate into two phases, right? What will it look like? It will look like this. What happened to the free energy now? It went up. That's all I'm trying to say, right? Over here, the free energy goes up. But if you're inside the inflection point, the free energy goes down. So it's simpler than what. So over here, if you try to separate into two phases, like a combination of this and this, the free energy goes up, right? If my arrow makes sense. It's only inside these 2 points that tiniest amount of fluctuations leads to free energy going down. It's not thermodynamically stable, but that's what you will see. So, and I will draw it on the next page and then I will shut up. So if you look, and sometimes these things can be kinetically stabilized. So even though it's not thermodynamically stable, you might see it for very, very long times. So nucleation and growth versus spinodal, if you look at the structure of the phase separated material, it's going to look something like this. In nucleation and growth, you will have alpha rich phases, you will have beta rich phases, all of them coexisting together, okay? In spinodal decomposition, you will have bizarre things where there is long alpha just went like this and there is a tiny beta that existed. It's at all scales. You can see phases existing at all length scales, and it looks more like a fractal. That's where I'm going to stop. So what's the take home from today? I talked about two types of phase diagrams. I talked about fully miscible phase diagrams, which lead to a length structure, right? And it comes from free energies, which are fully miscible. You saw how these free curves move up and down. Then I talk about partially miscible liquids, where you get phase separation. As you saw at any configuration, you have two phases existing. What I did not tell you about is why does this region shrink more and more as you increase the temperature? We actually already did that. If you go and look at that note, so I'll leave that to you. And in the middle, I talked about the kinetic factor. So if both of these are phase separated, and if you wait long enough, you won't be able to tell the difference. But if you're not waiting long enough, if you're not reaching the thermodynamic limit, you might find that the structure inside the blue one looks like a fractal, while the structure between the blue one and the black one does not look like a fractal. And the reason why the structure inside the blue one looks like a fractal is because in between these two inflection points, anytime you drop down, the overall free energy goes down. While over here, if you try to split into two concentrations, the free energy will go up. Unless you have a very big fluctuation, which automatically takes you to here and here. That's nucleation and growth, okay? So next time, we will talk about Lever rule, which is going to, I emphasize that when you split into vapor and liquid, the concentration of the vapor that forms is the same as the same, irrespective of whether you are splitting here, here, or here. So we will quantify this a bit more with Lever rule, and then we have 1 or 2 topics left and we'll finish up. The final homework is out. The final homework is very easy. If you understood these 2 things, the first point problem should be super easy. It's 60 points, slightly more complicated. The second problem is just van der Waals derivation, whatever I did in class, which has already repeated. Please try to score 100. Yeah.
So if you're between the principal gap and the spinodal gap,
Mhm.
then that system is thermodynamically stable and monochrome fluctuation.
It's kinetically stable. Thermodynamically stable means in the thermodynamic limit, you won't see a difference. It will just look the same. You will have one big alpha and one big beta. That's it. It's in that middle region. This is not, yeah, we have to use, it's the free energy lowers. That does not mean it is thermodynamically stable. The reason it is not thermodynamically stable is because thermodynamic stability will happen only when the chemical conditions are same, right? This and this have lower free energy, right? But they cannot coexist. The reason they cannot coexist is because this one has chemical condition here, this one has chemical condition here. They are not going to coexist. So they say, you know what, we can't coexist, but why don't we fluctuate even more? And they keep changing until they get to this point. So that's why it's lower the free energy. That does not mean it's thermodynamically stable, because that would require chemical potential. So in the thermodynamic limit, spinodal gap and miscibility gap look the same. In the kinetic limit, they make a difference. And none of us are in thermodynamic limit, because in thermodynamic limit, you know what will happen to us, right? We're dead. So we are all kinetically stable, right? I mean, that's just philosophical anyway. So it's important. And you can read up more on it. If you don't, I mean, just go and look up literature, first of all, on common tangent construction by Maxwell, and it will hopefully explain better what I did, even though I do think this should be clear. And also look up literature on spinodal gap and miscibility gap. I won't ask you exam questions about spinodal gap, but I would expect you to understand why did phase separation happen, not the kinetic part. That's okay. Okay, see you next class.
I have a question.
Oh, yes.
No, everyone can. Just regarding the homework. So when we do the graph, it's regarding activation energy, right?
Uh-huh.
Okay. That's cool.
When can we